All right, hello and welcome. My name is Elizabeth Angel. I'm the Communications and Program Manager at EERI. And thank you for joining us for this quick Quake briefing on the Indonesia M6.2 earthquake in February. We have a great group of speakers here today. Before we turn it over to them, I'm going to just take a minute to talk to you about EERI. EERI is the leading nonprofit membership organization dedicated to connecting professionals from a wide range of disciplines who are working to advance earthquake resilience in the United States and around the world. We'll share more information later, but I encourage you to look at our website and to think about joining us if you'd like to support this work and gain from the networking opportunities and perspectives we provide. I'm going to hand it over now to Volkan Sevgen, who's the president of EERI's Northern California chapter, which is hosting this quick Quake briefing. Volkan?
Hi, everyone. I would like to welcome all of you on behalf of our chapter and behalf of Earthquake Engineering Research Institute. This year, we started Quake briefings program to learn from experts around the globe to help each other's mitigating earthquake risks. And if you'd like to get involved with our community, I would recommend and I would invite all of you to go on our website and learn about our activities, suggest activities, and be an active participant of our efforts. If you have any questions and if you like to be part of our emailing list, you can email to our secretary and treasurer, Bruce Mason, and he will put you on our email list. And I would like to hand it to Bruce. Go ahead, Bruce.
I would like to welcome everyone to our briefing on the magnitude 6.2 earthquake that occurred in Indonesia on February 25th. My name is Bruce Mason, as Volkan mentioned. A few comments about future briefings. We intend for our briefings to be completely open to anyone who wishes to view them. We advertise them primarily two ways. The first is in the Pulse, that is the newsletter for EERI. And if you're a member of the Northern California chapter, you will receive email announcements from us. But if you're not currently a member but want to get the announcements, please send me an email to this address shown here. Or better yet, join EERI. It has many, many good benefits other than the quick Quake briefings that you're seeing today. But before we get started, I just want to mention our next briefing that we're planning. It will be on the magnitude 7.3 earthquake that occurred offshore Japan on March 16th. This earthquake has interesting aspects. The hypocenter was 30 miles down, but yet it had fairly intense shaking at the ground surface in Japan. A peak of ground acceleration of 1.2 G was recorded, and many sites had 0.5 G peak ground accelerations, surprisingly high for such a deep earthquake. Also, the famous bullet train in Japan derailed, even though they have early warning system there, apparently could not stop the train in enough time to avoid derailment. So we're lining up two speakers from Japan, and we anticipate having this briefing in early June. So look for the announcement in May. Now back to today's presentation. Indonesia has the world's largest island nation. It experiences a very high rate of earthquakes. It has on average magnitude 5 or greater earthquakes more than once a month. Indonesia's also had 5 magnitude 8 or greater earthquakes over the last 20 years. This seismicity is much greater than what we see in California. So we have two speakers that are joining us from Indonesia. One from Indonesia, and I believe one is from Saudi Arabia, because he is traveling currently. And they will tell us about the February 25th earthquake that struck on Sumatra Island. So today's format, it's a 60-minute program. Each speaker will talk for 20 minutes. We'll have a question and answer period after. We encourage questions from the audience. Behind the scenes, Volkan will compile the questions, and he will come back later in the program and pose the questions to the speaker. You will ask questions using the Q&A button that you see at the bottom of your Zoom screen. Now, we recognize we have more questions. We could have more questions than we have time. So each of our speakers today has kindly provided their email address that you see here, and they will try to answer your questions in the coming days should you email them directly. Now, I would like to introduce our first speaker. This is Dr. Ann Sirait. She will present on the earthquake mechanisms from the February 25th earthquake. Ann, could you please proceed?
Thank you, Bruce. Thank you for the introductions. Allow me to share my screen. Everybody, as Bruce mentions, my name is Ann Sirait. I'm come from Indonesia. I'm currently working as assistant professor in the Department of Geophysics, University of Indonesia. And today I'm going to share about the magnitude 6.1 Pasaman earthquake, which occurred in February 25th, 2022 in the West Pasaman, West Sumatra, Indonesia. In compiling this presentation, I also got a lot of help from Dr. Daryono. He is working in the BMKG. BMKG is a National Earthquake and Tsunami Center in Indonesia that kind of monitoring all the earthquakes and all the tsunamis that happens in Indonesia. So I'm going to start my presentations. In this presentations, I'm going to talk about the regional setting and the seismicity of the area when the earthquake occurred, and also I'm going to talk about the earthquake mechanisms, more detail on that, and then the possible source of the earthquakes, and then I'm going to make some conclusion based on based on what I'm presenting here. So for the first slide, maybe the third slide, sorry, I'm going to talk about the regional setting and seismicity. So this is kind of the map that's showing us the Sumatra Island and the Java Island. I'm going to showing you this map because these two islands is part of the Sunda Arc subduction zone, which in Sumatra is an oblique subduction zone, and while in the Java is a more orthogonal subduction zone. So as you can see here, this is the area is a very active deformation front, and the black arrows here showing us the subduction rate either in the Sumatra or in the Java. As you can see here, looking at the value, the Java part is a lot faster than the Sumatra part, and maybe you can see that we have a subduction zone here, and also in the Sumatra part we have a Mentawai fault zone. It's between the trench and also the island arc, and along the island arc we have the Sumatra fault zone, which is kind of like intersecting or dividing the Sumatra island, like from the north west toward the southeast part of the Sumatra. And I'm gonna also showing you the Sunda Strait. I kind of pointing out, zoom in on that part of the area. It's an area that connecting Sumatra and Java, and this is the area where this the former Krakatau volcano mountains exists, and then when it's like gonna explode, it's now the complex of the Krakatau is consists of Sartung, Panjang, Rakata, and Anak Krakatau. And I think maybe you have ever heard, but like a few days back, there is some activities in the Anak Krakatau that it's very close to the population, so it's still being monitored by the BMKG, the National Earthquake and Tsunami Center. So that's kind of showing you all the parts of the Sunda Arc subduction zone. And then we're going to talk more detail about the Sumatra. This is mapped from Nata Wijaya 2017. This is showing us like a more detailed zoom in about all the major fault that exists in the Sumatra, either in the offshore or the onshore part of the Sumatra. So we have the subduction zone, and also we have the Mentawai back truss that's located between the trench and the island arc. And while in the onshore part, there's a line that's stretching from the northwest to the southeast of the Sumatra, which is sorry, pick some laser pointer that here from the northwest toward the southeast of the Sumatra that kind of like cut all the Sumatra part. Yeah, so in the general itself, the Sumatra sits atop of the Southeast Asian plates, which converges the subducting Indian and Australian oceanic plate, and it's converged obliquely for about 50 to 70 millimeter per year. It's based on the research by Prawiro Dirjo at the year 2000. And the oblique convergence itself is partitioned into two components: the deep slip, which is accommodated by subduction interface, and the strike slip component is accommodated largely by the Sumatran fault zone here. Okay, and then so this is this is kind of showing us all the maps and all the map of the Sumatra and all the major fault in the trench in between in the 4 arc regions and also in the onshore part of the Sumatra. So if we talk about the seismicity of the Sumatra, this is map that kind of showing us all the epicenter distribution of the earthquakes of the Sumatra and its surroundings. It's the data from 1963 to January 2022. And as you can see here, that the seismicity in Sumatra is spread from the outerized regions, from the mega thrust zone also, and also along the Mentawai fault, and also in the onshore part is in the Sumatra fault zone. As you can see here that in the either outerized or in the mega thrust zone, the magnitude is up to like 9, with the depth like mostly less than 100 kilometers. While in the onshore part of the Sumatra, where the Sumatra fault zone exists, that the magnitude of the earthquake is, as you can see, is like about the maximum to 7, I think based on the circle size. And then also the depth is started from very shallow, almost 0 to maybe 100, 200 in this part of the area. And as you can see here, it also like goes down to 300 to 400 kilometer depth. So it's very, you can have it all. I mean, you have all the magnitudes like from small to great, and then you also have the depth is like from very shallow towards a very deep earthquake. And as you can see here, it's like kind of pointing out all the significant earthquakes that already happens in Sumatra. We have in 2004 is the magnitude 9.2 in Banda Aceh in the northwest of Sumatra. These earthquakes kind of excite tsunamis, and then it causing tsunami and take a lot of life at the time. And also we have in 2005, it's a magnitude 8.7 in the Nias Island. And we also have 8.4 in 2007 here in probably in the south of Sumatra. And in 2000, it's with the magnitude of 7, like near in the southeast of the Sumatra. But it have not been recorded yet, or maybe there's still no information about any earthquakes that happens within the area of this Mentawai Island with the magnitude larger than 7. And then it's close to Padang. Padang is the locations where close to the magnitude 6.1 West Pasaman earthquake. So as you can see that either although there's like lots of seismic happenings in this area, we still have a seismic gap that needs to be considered, need to be also monitored all the time. And next, you're gonna talk more detail about the active fault in Sumatra. So the Sumatra fault zone itself is extend about 1900 kilometers long, with the northwest and southeast trending, and it has a trench parallel orientations. And this is located within or near the active volcanic arc, bisecting the Bukit Barisan, the Sumatran mountainous range. And the mechanism of this fault is dextral strike slip fault zone. And The Sumatran Fault Zone itself is segmented into 20 major segments. As you can see here, we have Aceh Central, Bate, Tripa, Rendun, Toru, Barumun, Angkola, Sianok, Sutiti, Sulak, Dikit, Ketaun, Mana, Kemuring, and Semangko. And the red star here is the epicenter of the 6.1 West Pasaman earthquake. And the Sumatra Fault Zone is segmented into 20 major segments, and it varies in length between 35 to 200 kilometers length. And on average, a major earthquakes that occur along the Sumatran Fault Zone is once over every 5 years. So every 5 years, we always expect there's going to be one major earthquake happening in that fault zone. And then this is like more detail on the information about in the segment. It's kind of showing us the locations, the length, and then the large historical earthquakes that occur in that fault segment. Also, we have nature of southern termination. So and southern terminations, and then also you have a geomorphic features. Where is the locations of this fault in the geomorphically, and then we have a distance from the formation front. The closer one is 115, and then the farther one is like 323 kilometers, with the depth of two Benioff zone is ranging from 50 to 140 kilometers. Sorry, to 165 kilometers depth. So this is like more detail, and then you can find this information in this based on the research of Sieh and Natawijaya in 2000. This is another map that kind of showing us all the active fault along the Sumatra fault zone, and all the numbers, and here is showing us the slip rate and the earthquake potential of each of the active fault. Let's say I take some example, the Angkola segment. There's a potential to generate an earthquake with the magnitude 7.7, and the slip rate is 6 millimeter per year. And also we have probably the segment of Sianok here with the earthquake potential magnitude up to 7.4 with the slip rate 14 millimeter per year. So the purple box here kind of showing us the locations of near Pasaman, or near the earthquakes that occur in the February 25th, 2022. So based on the record from USGS, there's like few significant earthquake that happens there. It's in June 28 in 1926 with the depth 15 kilometers and the magnitude 6.7, and in March 6, 1977 with the depth 22 kilometer with the magnitude 6.0, and the other is like March 26 in 2007 with the depth 19 kilometers with the magnitude 6.4. And the last one, maybe not the last one, maybe the current one is like in the February 25th, 2022 with the depth 10 kilometers with the magnitude 6.2. So this is like the area that probably close to the Angkola segment and the Sianok segment. And then next, we're going to talk about the earthquake mechanisms. So this is like the basic informations of the magnitude 6.1 West Pasaman earthquake. So it's happened in Friday, February 25th, 2022. It's early in the morning in Indonesia, in local time, with the main shock magnitude first is calculated to 6.2 and then revised to 6.1 magnitude. And the epicenter is located in 0.15 degrees north, 99.98 east, and located 17 kilometers northeast from West Pasaman, West Sumatra. And based on the analysis, the hypocenter is considerably shallow. It's 10 kilometers. Okay, and then this is also showing us the focal mechanisms and the rupture time. It is from the IPGP website. the focal mechanisms of these earthquakes is dextral slide slip, which is consistent with the mechanism of the Sumatra fault zone. And the source time functions that showing us in this graphic is show the moment rate that are being released over time. And then as you can see here that the biggest moment rate is being released is at 4-second time. And the full durations of the energy release of this earthquake is up to 6 seconds. And then this is also showing us the column stress change of the magnitude 6.1 West Pasaman. As you can see here, there's the red color is showing the increase of dominant stress, and the blue the decreasing of dominant stress. As you can see that there's an increase of dominant stress toward the northwest and the southeast direction of the epicenter, which is it's being colored with the red color. And then there's a decrease of dominant stress to north, south, and east-west direction from the epicenter, being colored with the blue color. And it seems like it's very consistent with the distributions of the earthquakes or aftershocks after the main shock itself. And of course, there's a change in the column stress, and it will add more stress to the permanent tectonic stress of the seismogenic fault system, and it also disrupts fault mechanical condition of its surrounding. And this is information about the foreshock and aftershock activity. So this is map kind of showing us the seismicity around the epicenter. So the black star is the main shock. There's like a blue beneath the blue circles beneath the black stars that showing us the aftershocks of this earthquake. The foreshock of this earthquake. And then the yellow is yellow circles is showing us the distributions of the aftershocks, and the red one is showing us the background seismicity of this area. So there is a foreshocks that it occurs 4 minutes before the main shocks with a magnitude 5.2, and the MKG is recorded about 206 aftershock by Thursday, March 3rd, 2022, and almost a week after that, in March 9, 2022, BMKG records 230 aftershocks by Wednesday. So based on this number of aftershocks with the magnitude 6.1, this is considerably a very high productivity of aftershock of this main shock. So this is just kind of show you the aftershocks numbers of each day. And as you can see here that about 10 hours, 24 hours after the main shocks, we have 36 aftershocks, and then it's decreased to 14, but somehow it's increased to 50, and along the time to like a week after that, it's the number of aftershocks is decreases. So maybe I'm going to need to translate this to you that it is say that the total aftershocks is 230, and then the number of aftershock or shocks that being felt is 10, with the magnitude minimum is 1.4 and a maximum magnitude is 5.1. And next, I'm going to talk about the potential source of magnitude 6.1 West Pasaman earthquake. So this is showing us the distributions of relocated earthquake of the foreshock, main shock, and aftershocks. As you can see here that it's kind of like located like in the north part of the Sihanouk segment. So it may be say that this earthquake and also the aftershocks following the main shock is north extensions of the Sihanouk segment. Geologically, these extensions exist but not mapped yet. So the seismicity of these extensions is revealed after the West Pasaman earthquake. And this is also another analysis of the result of the relocation result, and then also kind of showing the similar result of the seismicity cluster that being spread from northwest to the southeast, and then with the length of about 20 kilometers. They assume that it's probably, other than it is the north extension of the Siano Fault, it's also probably like a new fault segment that being triggered by the West Pasaman earthquake. BMKG, sorry, named the new segment as Talamau segment. And then, so in the conclusions, so in an active fault near the population is the real threat in the subduction zone system. So probably in the, as maybe in the information that you get, this happened in the near population area, resulting in the destructions of houses, building, religious places. So it's gonna real threat in the subduction zone system. And then the West Pasaman earthquake also revealed unmapped active fault, but unmapped active fault which is existing geologically. And most important is we still need identifications of active fault in Indonesia, in particular, since there's other significant and destructive earthquake, either happens in the 2019, in 2021, in Ambon, in Ampana, or in Flores that caused by an active fault that is not yet unmapped. So that's all for my presentations. Thank you for the time and the opportunity. I'm giving back to Bruce. I'm going to stop share this.
Thank you, Anne. I want to thank you for a very comprehensive presentation today. I was struck by the diversity of fault systems that you have to deal with. And on one regard, it feels like we're earthquake wimps here in California compared to some of the challenges you face in Indonesia. Now I'd like to introduce our second speaker. Dr. Aswani Imran will present on damage to the built environment. Could you please proceed?
Okay, thank you, Bruce. Good afternoon or good evening, everybody there. Yeah, my title, my presentation entitled Building Damage to the West due to the West Pasaman earthquake, West Sumatra. It is prepared by me and also my colleague, Dr. Arya Mariani from ITB. Yeah, these are the outline. Yeah, this is a bit introduction of the most affected area due to that earthquake, which is the West Pasaman Regency. It is a regency of West Sumatra, Indonesia, with the total area of around 4,000 kilometers square, with a population around 450,000 people. Yeah, the regency administration is located at the town of I forgot the name. Okay, yeah, I think Anne already briefed you quite a lot, yeah, on this on the earthquake or the seismicity at West Pasaman. The magnitude is 6.1 moment magnitude. Yeah, please note that this magnitude is still lower than what it is used. Yeah, when we derive the seismic hazard for design in Sumatra. I think it is also outlined by Ain that there are some segments in that area with the magnitude greater than 7 even. Yeah, like Sianok is around 7.4. I think another segment close to Sumani around 7.7. Yeah, so that's actually the magnitude used in the derivation of seismic hazard of Sumatra. Yeah. So again, yeah, what happened last time is actually still below the expected, yeah, in that region. Okay, the right-hand side picture shows the shaking map, yeah, of the affected zone due to that earthquake. Actually, the intensity, yeah, the maximum is around 6 to 7. Yeah, that tall, yeah, due to this earthquake is around 19 people, and injured is 425 people. Okay, next, please. Yeah, this is a bit some more explanation of the intensity felt, yeah, due to that earthquake. Yeah, I think the most is felt in West Pasaman region with the intensity from 5 to 7. Surrounding area like Agam, Bukit Tinggi, yeah, only about 4, yeah, modified Mercalli intensity. The pesisir selatan is the area in the southwest of the affected zone. The intensity only about 2, yeah. Okay, next, please. Yeah, the next one I like to highlight some structural and non-structural damage, yeah, due to ground shaking. Okay, next. Yeah, before that, I'd like to brief a little bit about the popular structural system that used for housing, yeah, and also low-rise building in West Pasaman. Next. Next, yes, next. Next. Yeah, actually, for the old building, they're usually made of wooden frame, yeah. But the recent one, like the modern building, yeah, most of them are built using a masonry type of structure, either unconfined or confined masonry or concrete frame with masonry infill. So this is getting more popular recently, this kind of structural system. Yeah, the reason is because it's considered more durable and also more secure. Yeah, but the problem, the material is heavy and also brittle. Okay, next. Yeah, this is the summary of the house and building damage, yeah, due to the earthquake. This is recorded right after the earthquake. Actually, the most affected area is the West Pasaman, yeah, Regency, with the total heavy damage of 100 buildings, and the light damage is around 300. But then next, after that, this data is verified on site, yeah, and this is the next, please. Yeah, this is the summary of that. Yeah, the total heavy damage of house reaching 770 units. Yeah, moderate damage 3,000 units. Yeah, light damage is about 1,000. In total, around 5,000 damage. Yeah, sorry, 5,000 house. Yeah, experienced light or moderate or heavy damage. Yeah, and other facility like educational facility also experience some damage. Yeah, health medical facilities. Yeah, place of worship, yeah, and also government offices. Yeah, but the most affected by this earthquake actually the house actually. Okay, next. Yeah, this is the example of house damage, yeah, experienced due to the earthquake. The bottom right pictures there, it is showing the typical, yeah, house, yeah, built recently in yeah, many area in Indonesia actually, where people like to use like architectural columns, yeah, for their house, yeah. This column actually is not designed to resist the earthquake, yeah. It's only designed to resist the gravity load, yeah. It's a very good, it has a good shape, yeah. That's why people like to use this in front of their house to carry the heavy canopy, yeah. So then when the earthquake come, yeah, the heavy canopy, because the mass is so significant in that area, will induce, yeah, a lot of inertia forces, yeah, due to the ground shaking, yeah. And then the column not able to carry that load, yeah, from the earthquake. That's why then it failed, yeah. This is always happen, yeah. Every time the earthquake struck the area with this kind of typical house, yeah. So a heavy canopy, also sometimes the inadequate, incomplete tie element in masonry walls, yeah. Sometimes the tie element space so far, yeah, The ideal one is 3 meters, yeah, between the tie elements. But sometimes people just put every 5 or 6 meter, so it's too far. Inadequate maintenance, yeah, you can see from the picture on the left hand side there, yeah, the color already changed, yeah, it shows some sort of deterioration, yeah, in the construction materials, yeah, because of inadequate maintenance, yeah. And also, if you see on the top there, the roof structure, yeah, the supporting system is not that good, yeah, it is unsound, yeah, inadequate attachment and also incomplete elements, yeah. The tie element on the bottom there is not connected to the rafter, yeah. So it's a lot of this kind of things you can see on site, yeah. And it of course will cause some fatality, yeah, when it is struck by the earthquake. Okay, next. Yeah, this is another example of house damage. Yeah, it's almost total collapse. Yeah, the problem here is the roof structure is inadequate. Yeah, I think it has a similar kind of form like the one that's just shown in the previous slide. Yeah, that the roof structure is not is unsound. Yeah, the tie element thereafter is not connected well. Yeah, so that's why due to the shaking, it's just easy to fall down. And in addition, actually, the supporting element, yeah, the masonry wall also not equipped with enough or adequate tie element. Yeah, as I mentioned, that sometimes people just put the tie element every 6 meters. So in that situation, the masonry wall becoming unconfined, and because of that, it is very vulnerable, yeah, to the out of plane motion. So this, as you can see on the picture there, the wall just failed because of the out of plane motion. Yeah. Next, please. Yeah, this is another example. Yeah, similar type of failures. Yeah, because of the inadequate tie elements in the masonry walls. Yeah, and sometimes the tie element is not there. Yeah, sometimes. Yeah, sometimes it is not adequate, and sometimes some are missing. Yeah, so it's not complete tie elements provided around or surrounding the masonry wall. Okay, next. Yeah, yeah, this is the interesting pictures. Yeah, on the right hand side there, this is the most one of the most that experienced almost total collapse. Yeah, due to the earthquake. Yeah, this is one of the big most in the area. Yeah, I think the name is Karai Mos. Yeah, so the right hand side there showing the most before the earthquake. Yeah, if you can see there that the background is the old mosque. Yeah, so the main part of the mosque, which is the old one, is built in 1901, and then it is made of wooden frame. Yeah, the one that looks larger, yeah, on the background there. And then in the front side, it is the new one actually. Yeah, it is made of masonry type of materials and also concrete materials. Yeah, and then because of the earthquake, yeah, actually the one that fails is the new one. So the failure of the new part of the mosque, yeah, pull the old one. Even though if you can see, yeah, the one that I circle with the red circle there, that's the old one, still standing there. Yeah, but some part already experience some damage because of it is pulled, yeah, pulled by the failure of the new part of the mosque, which is made of heavy materials. So the new part has a concrete deck, yeah, on the top, yeah, with the heavy ornament on top, also made of concrete and also masonry materials. Yeah, and this is of course will attract, yeah, higher seismic demand, yeah, because of the ground shaking. And unfortunately, the column capacity is not there, yeah, to carry the additional load due to the earthquake. Because of that, it just fail and then collapse. Yeah. Okay, next. Yeah, this is another examples of damage, yeah, of public facility. This is one of the schools, yeah, in the area. Yeah, if you can see there, the front part, yeah, of the school heavily damaged, yeah, due to the ground shaking, but the back part still intact, yeah, still survive. Yeah. Now the front part there, if you see, the column is like freestanding. Yeah, actually, at the beginning there are connecting beams, yeah, between the columns in in three directions. I mean, yeah, but unfortunately the beams just fail because it doesn't have enough anchorage into the column. So the beam to column connection is not there. The beam rebars are not adequately anchored into the columns. So that's why, because of the shaking, it's just fall down. And then on the top of the beam, there is a heavy masonry wall. So the beam support the heavy masonry wall. So when the beam just fall down because of the inadequate anchorage, then the whole walls on the top of the beams also fall down. Yeah. Uh, Fortunately, the back part of the main part, I mean, yeah, the main part of the school is still intact, still in good condition. So only the canopy on in the front that already experienced significant damage, yeah, due to the earthquake. Yeah, and yeah, bad practice here is the also the fact that the two part of the building has a very different dynamic behavior, dynamic characteristic, but they connected, yeah, one to each other. They are connected each other, yeah, because of different dynamic behavior, of course, yeah. Then there will be some uh, incompatibility, yeah, of the deformation between the two. That's why it also caused some kind of failures, yeah, to the the weaker one, which is the canopy. Okay, next, please. Yeah, the next one, I just want to show some non-structural damage, yeah, occur due to the earthquake. Yeah, this is also typical kind of damage every time we got earthquake in Indonesia. Yeah, this is a government office, yeah, in the area where the ceiling, yeah, just fall down, yeah, due to the earthquake. So the problem here is that the ceiling is not designed to receive shaking, yeah, and they are connected, yeah, to the main structural element. Yeah, it is not supposed to be like that. Yeah, so if you have ceiling, we should have some gap, yeah, between the ceiling and the main structural elements, so that during earthquake the ceiling will not restraining the deformation. Yeah, if it restrain the deformation, then it's easily fall down. Yeah. Another problem with this building is that there is not enough diaphragms, yeah, that connect between the sides of between the side of the building at roof level. Yeah, you can see there at roof level there is almost no beams elements that connecting between the sides of the building. So in this situation, the roof frames will take up the load. Yeah, but the problem, the roof frame made of light steel frame, which is very thin. The section is very thin, sometimes only 0.5 or 0.6 mm. Yeah, so if it takes the load, especially the compression, it will induce buckling. Yeah, that's what happened there. Yeah, most of the elements, yeah, in that roof frame already experience buckling. Yeah, because of the out of phase movement of the sides of the building. Okay, next, please. Yeah, this is another example of almost similar situation. Yeah, the ceiling is restraining the deformation, and then no rigid diaphragm. Yeah, for the large span like the one shown in these pictures. Yeah, I think the span is about 12 meters something. Yeah, and then they only rely to, for the compatibility of the movement between the sides of the building, they rely on the steel frame on the top. Yeah, and fortunately in this building, the roof frame made of regular steel, not light steel frame, yeah, but the regular one. So it can still take off the load, yeah, due to the movement between the sides of the building. Yeah, but again, because the ceiling is attached, yeah, to the sides of the main structural elements, then it restrain the deformation. Because of that, it just fall down, yeah, because it doesn't have any strength, yeah, to resist any movement, yeah, any relative movement between the sides of the building. Okay, next, please. Yeah, this is just a closure, yeah, from what I just present. One is yeah, the cause of the building damage is the poor structural system and poor design. Yeah, actually, we have already have quite comprehensive building codes, yeah, that regulates the proper structural system for the area that has a high seismicity zone. Yeah, so but sometimes it is not implemented properly. Yeah, in practice. Seismic detailing is sometimes inadequate. Yeah, as shown before, the anchorage of the beam rebars is not there. Yeah, so under gravity load, sometimes it is okay. Yeah, but when the building experience some shaking, it's just easy to fall down. Yeah, inconsistent construction, especially related to material and construction quality, and also consistency with design. Yeah, sometimes the design already there, already comply with the building codes. Yeah, but when it is but when it comes to the construction, a lot of deviation, yeah, from the design. Yeah, no consistency between the construction and the design. Yeah, inadequate maintenance. Yeah, as shown also in the previous slide. Yeah, that induce material deterioration and cause, of course, some weakness, yeah, in the building. Yeah, seismic demand is sometimes too high due to many factors. Yeah, structural irregularity. Yeah, unisolated non-structural components. Yeah, like shown in the ceiling there. The structural non-structural component is not isolated. Yeah, it is connected to the structural elements. Yeah, unnecessary mass. Yeah, sometimes we put so much significant mass, yeah, in our structures in the form of ornaments. Yeah, or sometimes the structure itself. Yeah, like the concrete decks, like shown in the previous slide. Yeah, so heavy. Yeah, but the supporting element is not adequately designed, yeah, to carry that heavy concrete decks. Thank you.
Thank you, Dr. Imran. I really enjoyed your descriptions of the damage. It shows how these damage modes are really universal. You showed false ceiling failures. You also showed how masonry can fail, and you showed how wood structures perform well. That's been observed, it seems like, everywhere. That ends the presentation part. I would like to turn control over to Vulcan to ask questions of our speakers. Vulcan, can you please proceed?
Thank you, Bruce. Thank you, Anne, and thank you, Isvandi. These were great presentations. My first question, in fact, you have probably seen it in the chat box about the liquefaction observation in this earthquake. Were there any experiences of liquefaction, or liquefaction was most unobserved?
Thank you for the question. So there is no liquefactions occurred due to this earthquake, but there's a collateral damage about related to the landslide in the hill near the mountainous range, and it's being recorded and also being observed. So there's yeah, mostly it's the landslide and also the flood due to the earthquake.
Flood?
Yeah.
Or maybe that's part of the liquefaction, I'm assuming.
I think it's just because like the local aquifer is kind of ruptured during the earthquakes, and then it's kind of like water come up to the surface and it's creating flood. But not there is no liquefactions.
All right, so that's great. I have a question for Isvandi. You mentioned about that mosque that was built in the early 1900s, and then there was an addition.
Yes.
Presumably newer structure. Do you know when was that structure added to the mosque?
I think after the 1960 or 1970, so they built it in staging actually, not in one stage. Yeah,
I see.
I think there are many staging of the construction. I think 3 or 4 times or 5. I forgot the numbers. That's what I heard from the people there. Until they got the end shape like what they had before the earthquake. Yeah, but the yes, okay.
Were the seismic codes adequate at that time in Indonesia, or they were improved later on?
Yeah. Actually, the seismic code always improve. Yeah, but before 1970, the earthquake code is not there yet. Actually, yeah. We start to have the earthquake code at I think in 1970. Yeah, and then the detailing requirements just come out I think in 1980 something. Yeah, sorry, 70 something before the sorry. Yeah, I think before the late 70 we have already have some quite comprehensive detailing provision, yeah, for seismic design. Yeah, but not as comprehensive as what we got now. Yeah, now it's even more comprehensive. Yeah.
Do you have distinction between high seismic zone, low seismic zone in terms of building code requirements, or do you have a uniformly high seismic zone seismic codes for the structures?
We have I think 4 division: low, very low, moderate, and high. I think we are similar like the one in the ACE 7, yeah, where we have like a seismic design category. Seismic design category A, B, that's considered low, very low. A is very low. Sorry, yeah, A and B is very low, and C moderate. Yeah, D, E, F is high seismic zone. So similar, but we start to have that kind of category, I think, in the late 2000.
Late 2000.
Just recently, so probably 20 years ago. Yeah. Before that, we have bit different category. We categorize the seismic hazard based on the seismic zone. Yeah, based on the PGA values. Yeah. At that time, we have a 6 category of seismic zone in Indonesia, from the very low to the very high.
Great. Do you have a sense or any measurements about the damage and observed PGA for those locations?
We don't have.
So you don't know exactly what would be the PGA?
No. For this particular one, no. I haven't got any data yet. Yeah, for this West Pasaman earthquake. Yeah, we got data from other earthquake like the one in Palu. We have some data, but for this particular one, we don't have the data. Probably BMKG, the one the agency for the earthquake and tsunami mentioned by Dr. N. Probably they have some data regarding the PGA values. Yeah.
Let me ask, Anne, have you observed any power outages in this region due to this earthquake?
Sorry, I think I don't see any, like, I mean, I haven't seen any record there's any power outage there, just like more building collapse, and then also like landslides, or maybe just like flood, but there's no power outage recorded I have found there.
All right. So as you know, there was an earthquake in 2007, Padang earthquake. The question from Charles Scotthorn, how do you compare damages in this earthquake in this region versus the ones in Padang?
In Padang is actually 2009, the biggest one. The biggest one in Padang is 2009 in September.
Okay.
Yeah, the damage is quite much larger scale, yeah, compared to the one we have in West Pasaman. And
even in this region,
even in this region, yeah. I think that's one of the damaging earthquake that we ever experienced in Sumatra, in addition to the one occur in Aceh actually.
Yeah.
Yeah.
All right. So let's see. Bruce, do you have more questions while I'm looking at the other questions?
Okay, yes.
Coming from the Q&A?
You know, I'd like to ask a question of Anne. It seems like when we have our quick quake briefings, seismologists always have some surprising aspect from an earthquake. Do you know what was surprising? Was there something that just struck the seismologist, said that we just would not expect this from this earthquake? Were there any surprises in the seismological community?
Okay, thank you. Probably the one that very surprised is because this main shock and also the aftershock distribution is not occur within already mapped active fault. So they're probably surprising. So it's mean that there's active fault there, but not being mapped yet. So it's kind of like inducing like more curiosity to probably do more work to mapping the active fault, not just in the Sumatra, but also the other part of Indonesia. Yeah, that's probably the most.
Okay, great. Thank you. This one's for Dr. Imran. With regard to masonry and wood construction, you mentioned masonry is very popular, yet wood has a record of better performance. In Indonesia, is wood just too scarce or it's just not used? Could you comment on that, please?
Yeah, one of the reason is that people consider the wood structure is not permanent structures. People also consider the wood structure is unsecure because it can easily be broken into. Recently, we have also problem if we want to build with the wood structures. It's very hard to find a very good wood materials, because now to get the very good wooden frames, for our buildings, we have to get it from sometime Kalimantan or from Papua, but it is very hard to get it because it is considered as I don't know, they call it preserved or conserved, conserved materials, and then because of that, if you still want to get it, it's very expensive.
I see.
The price. So the cost for wooden house is even more expensive than the masonry house. That's the problems.
Okay, but you would think that observed less damage in wooden structures might provide incentive. But I see your point with regard to cost.
Yeah.
Okay,
I have one question. I know we need to wrap it up, but these questions I'm just going to combine those. Maybe I can ask Anne. What are the kids learning from school in terms of earthquake safety? What kind of drills are they being conducting? And relevant to that, are there enough resources for people who would like to build their homes or find safer home, do they get any info from any government office?
Maybe I'm going to answer about the maybe like what the schools children do. I mean, like, yeah, I think it's already being yep, there's like institutions, there's some organizations that are also like do some community service to the schools regarding the disaster education for the children. I do there are some part of the in my university also working with that, but mostly we are working in the area that probably very prone to the earthquake. So there is an education for that, but I'm not sure how much I'm not sure about the detail or everything, but there's an education for that for the children's. Yeah.
Are the school buildings mostly concrete or they are masonry?
I think it's mostly concrete, sir. Yeah, is it that, Professor Iswandi? Mostly.
Yeah, mostly concrete frame with the infill machinery. Mostly. Yeah.
For example, with that earthquake precludes the main shock, like 4 minutes earlier. Like in the United States, we tell everyone drop cover and hold on. So that's a little bit of a problem when you have masonry infill.
Yeah. Yeah, I mean, we have the education for that too, but yeah, probably the problem is still in the building. I don't know.
Well, masonry infill will behave well if the tie elements, the anchorage is there. So sometime when you have main columns spacing of a 6 meter, for example, then when you introduce masonry infill there, you have to put additional practice column in the middle, so that it will tie the infill quite nicely. Otherwise, if you don't put there, then the out of plane will be very dangerous. Yeah, especially when it experience motion out of plane, it's just easy to fall down. And in addition, we have also some requirements that when you have the infill wall for low-rise building, that you have to have a good anchorage, yeah, between the infill wall and the frames. We usually provide the 8 mm rebars, yeah, coming out from the columns and go into the infill wall. So that's, we hope, can tie the can keep the stability of the wall, especially under out of plane motion.
Did you observe significant difference in terms of performance of unreinforced masonry, confined masonry, or frame infill buildings, or they were more or less performing the same way?
Well, if you design it properly, then it will perform the same way, I guess. The problem with the unreinforced masonry or the unconfined masonry is that if they have a very heavy roof materials on top, then it will introduce higher seismic demand during the earthquake. So the best way, if you still want to use this kind of system, like the confined masonry or unconfined masonry, unreinforced masonry, keep the weight of your roofs as light as possible.
Very
because
good.
that's the one that will attract the seismic forces during the earthquake.
So perhaps finally, more on a general terms, in terms of what we have learned in the last 20 years, observing these large earthquakes. In your mind, do we now see a better practice of structural engineering or construction and seismic design in Indonesia? And what are the current levels of seismic hazard understanding in these regions?
Well, I think we have to classify that into two main systems. Yeah, we call it non-engineered building and the engineered buildings. For the engineered buildings, yeah, things so far we are in good shape now. the understanding of the people involved in the construction or in the design of that building already understand what they have to design, what have they to do during the construction, the importance of the detailing, the importance of the 135-degree hooks for the confining reinforcement in the columns and etc. So they now getting more understanding on that they have to do that, even though it's very difficult to implement on site. But on the other side, when we're talking about the non-building structure, non-engineering building, that's still the problems, because sometimes just regular people or common people, they build their own house, knowing what is the best way to build this kind of house, especially when you are in the high seismic zone. So that's the problem. Still some problem in that aspect, actually, and in that regard.
If you like to put a percentage of it, what percentage of the buildings do you think are non-engineered and what percent is engineered?
Most of the house building actually non-engineered buildings.
Oh, okay.
Not many of the houses gone through the calculation or engineering calculation. But our governments, already now, I think the last 20 or 30 years, they already provide the some sort of manual, for earthquake resistant house. Where in that manual, it's already given the information, what is the minimum size of your columns, what is the space, the ideal space for the columns, what the numbers of rebars that you have to put in your columns, and etc. That's quite nicely placed already. So people just follow the manual.
Recipes.
Actually, it also rich of pictures and everything. Easy to understand actually, but not everybody doing that till now. So that's a problem.
Of course. Now I will first of all, let me thank both of you, and then I will hand the virtual microphone to Bruce.
Oh, okay.
Thank you so much.
Thank you. We're running a little bit over. I'd like to thank both of our speakers today for excellent presentation. I know we learned a lot. I'd like to turn control over to Elizabeth to close out the meeting, please.
Great. Thank you all so much for attending today. I've launched a quick poll. It's just a short post-webinar survey. We'd really appreciate it if those of you who are still here could fill that out and respond right now. If you want to learn more about EERI, you can check out our website, which also has information on how to join and the benefits of membership. I encourage you to check out the Pulse newsletter for information on future webinars. And there's a link again to the EERI Northern California website and mailing list. And finally, I just want to thank FEMA and EERI members for supporting webinars like these. That's what makes events like this possible. Thank you again so much. I'll leave the poll up for another 30 seconds or so for people to complete.